Welcome to the afternoon session. This invited talk will be given by Dr. KKanoun. She's a research director of French National Center for Scientific Research. She has been the IFIP Special Interest Group on Dependable Benchmarking. She is also involved in many conferences, including the chair of the steering committee chair of the European Dependable Computing Conference. And she has been on the steering committee, including DSN, ISRI, and CIRI. So she has been very active in European countries. So let's welcome Dr. KKanoun. You have.
Okay, I will try to.
You know this better?
So, my presentation is dedicated to software dependability assessment. And I expect that most of you are familiar with dependability, but I have noticed that the word that is the most used here is trustworthiness and trust. It used to work. So now it works. We can start again. As I told you, I have noticed that the most used word is trustworthiness here. It could be survivability. So to use a computer, you need to trust the computer, but on the other hand, you depend on this computer. And the aim of my talk is to show you and to maybe to share with you some approaches to trust in a computer because you depend in this computer. And I put emphasis, it is not too strong, no. For me it is. To trust the computers because you depend on them, and dependability is a generic term, and it has several attributes: availability, safety, security, maintainability, and so on. So I will not assess dependability per se, but I will show how to assess some attributes of this dependability as a generic term. And I put a question mark in my title. This means I'm not sure that it is a reality or a dream. Indeed, the conclusion will be it is a reality, but with some limitations, and our dream is to push these limitations. So now you have the conclusion of my talk. It is okay. Before starting my technical presentation, I wanted to share with you some statistics about Okay, so something is I don't know what is. Let me try again. Works. So I have selected on purpose telephone switching systems because they are among the first systems for which stringent, very strong requirements, dependability requirements, and indeed availability requirements have been put on. And I use in purpose have been because it used to be the case, it is not the case. And the requirements for dependability was an availability per year should be less than 3 minutes per year. If you can see the evolution, the past evolution, the 5 minutes per year were more or less respected. And since the evolution and since we have internet and cellular phone, the availability has dropped from 5 nines to 2 nines. And we are all aware of this, and we all accept the situation. Why? Because it is very, very convenient to have a cellular phone, even if it does not work all the time in several places, even if it fails, but we are happy to have it. So the perception of availability is indeed a trade-off between the convenience, the functionalities, and the availability itself. And now, this paper has been published by our colleague Jim Gray. Most of you know, most probably he passed away a few years ago, unfortunately. Here, we don't know what are the reasons of unavailability. It could be the software or the hardware. And here I give some examples of famous historical data. I will not comment on them at all, but just this selection of examples cover 30 years, from 80 to almost 2010. And the main topic of this slide is to show you that the causes of famous failures could be physical failures, the hardware, development, mainly the software, but it could be also development in the hardware, or interaction faults. And this morning, the invited speaker talked a lot about interaction faults and human faults. The impact of these failures could be localized or distributed, and they may impact availability or reliability, safety or confidentiality. And you can see that some of them impacted one attribute, some of them impacted 2 of them. I don't have any example of failure that impacted the 3 attributes. So it is important to cover all. And in some systems, some classes of faults are more important than others, and I give here 2 examples of systems, transactional systems or electronic switching system, as in the previous case. And for this, if we look at the proportion of fault, we can see at rank 1 comes development faults. 60% of faults are development faults. Whereas if we look at controlled systems, like in civil airplanes, on phone or on network or other application, we can see that the human interaction factors are in the first rank, followed by development, and then we have in equal space physical faults, internal or external. So we can see that depending on the system, some classes of faults will be more important than others. And just to finish with also with the statistics, here there is a study a survey that has been published by Ernst & Young a few years ago, and what they have done is that asked people who are working with system who lost some system availability, and they asked them to give the causes of incidents. And in most of 2/3, in 70, 75% of the time, hardware faults appeared as the reason, followed by internet worms and security, by telecommunication failure and software failure. I will stop here. So you can see 2 things, that even though we have the impression that security and worms, internet worms are the main reasons, indeed, they are in the same, at the second rank, but they are not far from. And software appears as one of the main reasons. The other thing is that if we group these according to malicious and non-malicious failures, we can see that 1/4 are malicious and the other non-malicious. Maybe it was done in 8 years ago. Maybe things have been changed. And even if things change, this means that we have equally or almost equally consequences due to hardware, failures due to hardware or to security or to integrity. What I want to say, I think this is good for this conference, and I think this is the way the conference really moved from integration to safety and security, because we are moving into a world in which both aspects, safety and security, are impacting our lives. In my talk, I will put emphasis on software failures, and I will share with you some approaches to evaluate software availability or reliability or safety. And most of the time, I will talk about a failure rate. So, why do we need to assess dependability? As a user, as users, all of us as users of systems, we would like to have confidence in the product. This morning, we talked about trust in the product. And having trust, it is good to have a qualitative trust, but it is better if we have some quantitative measures. And it is important to make sure that the failure rate due to the software is acceptable. So, as a user, it is all. I need an acceptable failure rate. As a developer of the software, it starts during the development process. I would like to make sure that by construction, I am reducing the number of faults. I have reduced the number of faults from the beginning. My aim is to optimize the development process, the testing process, and at the end, having an operational dependability that is high enough to be acceptable by the users. Then, when the software goes into operation, I have, as a developer or as a supplier of software, I have to continue to do some maintenance, corrections, and I have to plan this correction. And then for long term, my aim is to improve software dependability for the next generations, to learn from what I am doing now to improve my capacity to have better software from the beginning. To assess this dependability, there are few approaches. So one of them, which is the dream, I would say, assessment based on software characteristics. Just if you know the language, some complexity metrics, the class of application, then we will be able, we would like to be able to assess, to give a number of failure rate. But this is the dream. There are few work that have been done on this, and still we have good results, but still we are far from having really very nice package to estimate a priori the failure rate of the software. We can have assessment based on measurements. The figures I have shown to you are based on measurements, or based on controlled experiments. I will take my software, I will inject faults, I will push it into its limit to characterize its behavior. And in sometimes it is not possible to assess the software itself. So what we do, we will assess the production process because we hope that if the production process is good, the software will be good. And this is all of you, most of you have heard about CMMI, Capability Maturity Model, in which case we will evaluate the institution instead of evaluating the product itself. In my talk, I will consider the three approaches to dependability assessment, and I will not consider the first one. When you have a piece of software and you have some failures, then the faults are identified and are removed. This means that the software is evolving all along its life, and because of these corrections, we don't have a repetitive process as in hardware. Because in hardware, there is maintenance, and you have a hardware that is as new, as good as new, and then you continue. So we don't have a repetitive process, and it is very hard to find mathematical and statistical approaches to deal with this. There is no relationship between failure and faults. This means the software can have just a small number of faults, but they are activated all the time. The failure rate is very high, but it can have just only, it can have a large number of failures, faults, and that they are not in the operational profile path, and they are not activated. So this means there is no direct relationship between the number of failures and the fault. I will come back later to this number. The software is very sensitive to the user profile, and the user profile is continually evolving. Also, another difficulty comes from the fact some of you, and I have seen some presentation today about reliability growth models, these reliability growth models have been oversold when they have been developed. So people were disappointed when used them, and then they stopped using them. Another difficulty comes from the fact that for software reliability, we will use failure data observed on the software. And mainly, if it is in operation, it is easy, because it is not your software, you will be happy to write and to give information. If it is the developer who is writing, who is reporting the faults, he will take it as a judgment of his capacity or her capacity to write the software. So they will not show all the information. And finally, what is the meaning of software, of dependability of the software? Is it the number of faults? Is it the complexity of the software? Or is it the mean time to failure? And I tried here to show you, indeed, if we have software, the software, without being executed, it has complexity metrics, the length of the software, or the number of branches. We can have the number of faults that are in the software, or the fault density. These are qualified as statistic measures. However, when you use the software, you will use it under a user profile and under an environment. And so it is the combination of two that will give you the reliability or the dependability of the software. So you need to know both of them. So unfortunately, we cannot model and integrate explicitly the user profile. What you will do is that we will observe the software in its environment, and we will use the information in a combined way to estimate the failure intensity or the failure rate, the mean time to failure, etc. I will come back to this. So you can see that the number of faults is interesting, but as a user, I am also interested by the way I am using it. And just for illustration, this is data that has been published by IBM a few years ago. The columns give the percentage of faults in the software for which the mean time to failure is here less than 1.5 years per 1.5 per year. Here, the MTTF is between 1.6 and 5 years, and so on. So you can see that the percentage of faults is very, very low for the most frequent failures. And then we can discuss this offline or at the end of my talk, what is the meaning of 5,000 years of MTTF. This means that you have, if you have 1 million or 2 million of copies of the software that are used all over the world, if you have only one failure per year, the MTTF is more or less near to 5,000 than 5 years. So you can see this shows that it is important to take into account the operational profile. So what we will do, we will have software. The software is running. Either it is under test or in operation. And we will collect information, failure information on the software. Either the times to failure, or the number of failures per unit of time, the impact or the consequences of failure, the faults that are at the failure origin, and the corrections. So we will use all this and we will process the data. We don't need to do all this processing, but depending on what you are looking for, you can, for instance, do some descriptive statistics to have some correlations. You can analyze the failure modes of the software. You can analyze the trend. The trend, this means you are debugging a software, making corrections, and you would like if the software is becoming better and better or no. And then, which we are interested in here, we can estimate the mean time to failure, the mean time to repair, and the availability. To do this, we need some models to predict this behavior. And we can have non-statutory processes, for instance, non-homogeneous Poisson process to do it. This is related to all reliability growth models, stochastic models, and most importantly, we have to validate the models because we are not sure which models are good or not. Why? For instance, let's consider an observed failure rate, which is the dashed lines. This is the observed failure rate of the software. You can see that if we smooth it, the failure intensity, which is the frequency of failures, is decreasing, and we are happy because when we introduce corrections, the failure intensity is decreasing. Unfortunately, or fortunately, because sometimes we need to introduce new specifications, sometimes we change the environment, sometimes we change user profile, and because all of this, the observed failure rate, if it is smoothed, we can see that it increases at a given moment and then decreases again. And applying a model to the whole this behavior maybe and usually will not lead to good results. That is why it is very important to analyze the trend and to apply models in accordance to their assumptions. I like examples. Here, I consider the failure intensity of a real software switching system. We have studied, it is Brazilian. I know that people from Brazil, we have at least 1 or 2 attendees from Brazil here. No, they are not in the room. And the observed failure intensity is this one. The unit here is months. Indeed, I think that the first 3 months are not really, the software was not tested. And they started testing it, and as they had some feedback from another system, they stopped the test, and then they came back. It started really here, the 4th month, and you can see that the number of faults per month had been decreasing, then increasing, and then, which is interesting, is during operation, when the software was shipped, the failure intensity was decreasing. Here it is 0. Just, as I told you, this is a Brazilian switching system, and in France we would say it is August, because it is holidays. This does not mean that the telephone is not used. The telephone is used, but we don't record the failures. If there is any failure, we give priority to making things working again without recording the failures. It happens here, it was February in Brazil, Carnival. So, we know that there is something which was wrong here, but we have to accept to work with these figures. This is the observed failure intensity. And just to show you really that the reliability has been really improved, here the evolution of the number of systems that have been installed, they went from 1 to 42 at the end. This means that at the end here, you can see from 25 here, we have 42 systems, and we have small number of failures compared to here when we have only one instances of the switching system. If for the same system, it is the same data, I plot the failure, the cumulative number of failures. You can see here during validation and in operation, we can see that it was growing smoothly. Now, I would like to make some predictions. To do this, what I have done is that I have applied one of the reliability growth models. Here it is hyper-exponential models because we have worked on this, but we have also applied other models. It could be the S-shaped model, it could be, and we have applied them. My aim is not to show you that this model is good, just to show you what I have done is that I have assumed that we have observed the software until unit of time 20. And then I applied the model, and this is retroductive assessment. And based on this, we have made some predictions. This means that we have ignored all this data, and the prediction by the model gives this curve in red. This means, how do you use this? I am the developer of the software. I am CPKD, the company who wrote the software. The software is in operation. I have observed in operation after 10 months. And after 10 months, I have observed this, and I would like to be able to assess the number of corrections I will have to do. And the assessment gives 37 failures. Indeed, the observed one is 33. Here, we don't try to have precise things. We are engineers in the field, and we would like to have an estimation of the number of faults to dimension the team. So this is the way I will use the reliability growth models to plan maintenance. I can also use reliability growth models to assess the software failure rate or the software intensity. And I use the same model over the same period. I apply the hyper-exponential model as a measure of failure intensity. And we can see that at the end, the failure rate is almost constant, and it is equal to 5.7 10 minus 4. So this is the failure rate of the software. If you compare it to the failure rate of the hardware, it is usually 10 minus 4. So you can see that it is comparable to the hardware. We can go even further because the software, as you have seen in one of the presentations, maybe this morning, yesterday, is composed of several components. In this case, the software, it is telephone switching system. The software for telephony, and we have 3 other components. One component is interface with neighbors. One is for the management of the switching system. And the other one, which is very important, it is for defense. Defense, here is the name of the software that is in charge of fault tolerance of the hardware. This means this is for recovery if there is the hardware is redundant, and if there is a failure in the hardware, it will be covered thanks to the software, to the defense software. So we have applied the same model to the 4 components. And what we have done is we use the sum of these failures, the previous failure mode, and compare it to the direct estimation by the same model. And you can see that they are not far from each other. However, you can see that if we do the sum, the failure intensity is higher. Why? Because some faults will induce several failures in 2 or 3 components. So when we sum, we add the consequences of these failure rates. That is why it is higher, but they are comparable. We can go further. We have the failure rate of the telephony, which is almost 10 minus 6. It is small. The defense, 1.4, 10 minus 5. So you can see that we have an electronic switching system. The main function is telephony, and the failure rate of telephony is the lowest failure rate than the other components. This means that they put emphasis, when developing the software, they put emphasis on this one. And they debug it less the other components. For defense, it is normal because it is very, very hard to debug the fault tolerance mechanism. So, and if we add, we have. So here, this is what we have done for this electronic switching system, and I wanted to show you. It was not easy to do because there are some assumptions. We have to work on the trend and so on. But it works, and we can have some failure rates for the software, even if they are called systematic faults. And for this, the other software, we have used reliability growth models. So I can take another example that has been published by Musa from AT&T, and you can see here is the failure. This is the trend test. I will not show it. It is what is interesting because I have not talked. I have reduced my talk, so I have not. I am not talking about trend test. But just if I just plot the mean time to failure, you can see that for this software system, the mean time to failure is oscillating about an average, and this average is MTTF for the software. And for this software, it is an operating system, which is an operation. It was not corrected, and you can see that it behaves exactly like hardware with a constant failure rate. So we can use a Markov chain or a Markov model or Petri nets to assess the dependability of the whole system, taking into account hardware and software systems, and taking into account a constant failure rate of the software here too. So these results have been obtained based on observation of a real software in operation or during testing, and application of some reliability models, reliability growth or stable models. These models are very interesting at the end when the system is in operation. Like, during early validation, we will use just the trend. We will not assess software dependability because the testing is not representative of the operational profile at early validation phases, so we will just test the trend. At the end of validation, if we have a good operational profile, and if we have enough data, we can assess the dependability of the software, but the limitation is limited by the observation duration, 10 minus 3 times 10 minus 4. When the system is in operation, when we have tens or hundreds or thousands of systems, the assessment may lead to highly relevant results. And here I given 2 examples of systems. One is a French one, and the other one, I don't remember, ABB, it is European or international now. And we can assess failure rates that are, this is 5, 10 minus 6, or 10 minus 7 for critical failures. And for this nuclear instrumentation and control systems, they have observed 8,000 systems in the field over 4 years, and the observed failure rate is around 10⁻⁷, and for critical failures, it is around 10⁻⁸. So you can see that we can obtain good results if we have enough statistical data, but we can start have meaningful results if at the end of validation of the system. So with this, I finished the first part dedicated to assessment based on observation. And just to show that we can obtain good results. However, all is not done. Now we have new classes of systems, service-oriented systems, adaptive and dynamic software systems. We have seen this morning, they are becoming more and more important. And I think for this, assessment after fact is not enough, and it is maybe important to do some online assessment. This is, I think, one of the directions towards we have to go. It will not be easy to do it, but we have to do it at runtime, otherwise it will be too late to do it. To do this, we need the help of industry. Why? Because data is very confidential. Industry people will keep them. So it was very hard. We did some work for industry, but most of the time it was confidential. When we worked for Airbus, I am not even allowed to tell you that I worked for Airbus. The results were very good, but I signed a confidentiality agreement for 77 years. The student who did the work, she was 23, she told me, when I will be 100 years old, maybe for my grandchildren, I will tell them that I can show them the results for Airbus. And this is really it is a damage for us because for working it is very limited. So when we are lucky, we can collect data, we can do some estimation. Sometimes it is too late when we do them. So sometimes, mainly for off-the-shelf components, we would like to have more information and to have assessment of the software. So as it is not available from the developer of the operating system, what we can do is that what we call off-the-shelf components. We will do controlled experiments to do it. And this is what I will do later in the next. And I will come back maybe later for safety critical systems during development. Yes, I will come later for this. So we all know, and performance benchmark are very useful and they are used. I can't say that industry are very happy with them, because if they are not the first, they will not use them. And so I know that they dimension their system to respond to the benchmark to show that they are the first. And when we started working on dependability benchmarking, people from industry, and they were from Intel, from Sun Microsystems, Microsoft, IBM, they were all in the room and they wanted to share this work with us, either to progress with us or stop us doing the work. It was both, indeed. And because they were afraid. At the end, I am talking about a working group, I think a working group on dependability benchmarking. And at the end, we worked together. And in this framework, we have published the work on dependability benchmarking. And they all have a chapter in this. So this means that they starting just keeping us outside, and then they joined. So dependability benchmarking, we use it when there is no information available from the software development. And so what we will do, some controlled experiments. we will do some controlled experiments to learn more about the software. So either we do ad hoc, case by case, or standard. Ad hoc can give many information, very interesting information, but usually it is used for internal purpose, and we push towards standard results to be available to people from outside. And to do this, we have to, the benchmark should satisfy some productivity, some properties. It should be reproducible, repeatable, portable, representative, acceptable, with an acceptable cost also. Okay, so we started this work. I give here just small example on this. I would like to use, to build new system, and I would like to select the operating system. Which operating system to select? We can imagine a situation in which we can do some experiments on some existing operating systems, just according to the aim we would like to satisfy. The problem is that with these off-the-shelf components, like operating systems, we know the functions, the description of the function, but we cannot go inside. So we have a limited accessibility and observability. We can use only the interface that is available to the users. So we have to work in a black box approach. And what we have done, we started with a robustness benchmark. This means that we take the operating system and we don't change anything in the operating system. We will simulate application failures, hardware failures, or device driver failures. And the only thing we can do is to observe the outcomes of the software to characterize it. And in the results I will show to you, we have simulated application faults. So we intercept system calls, we change them, and then we observe the behavior and look at how the operating system reacts. Just examples of results. Here, Windows, Linux. We don't have Microsoft here? Okay. No. Brandon Murphy from Microsoft contributed to the study. So you can see that if I look only to the response time, we can see that the response time of Windows is lower globally than the response time of Linux. This is not enough. If I look now to the mean restart time, we can see that in some time they are comparable. In some times, Windows takes more time to restart. Indeed, if you go further and we look until all system calls that is corrupted, you can see that Windows and Linux do behave very differently, because there is a disk check for Linux and each 26 system calls. So that is why, system restarts. That is why the restart time for Linux is very high, each 26 restarts. However, you can see here for Windows that there is an average, and then there is fluctuation. And this is true for all operating systems, Windows operating system we have studied. And indeed, when we analyze deeply the reasons, this is the impact of the application state after failure. If the application is in a hung state, it takes more time to the operating system to restart. So we can see that the application may impact the restart time of the operating system, only for Windows and not for Linux. Just I showed you these results. We have much more results, but just to show you it can work, but there are some limitations. For instance, benchmark should not replace software test or software validation. It can be in addition. Should be done in addition. In our case, we had to be non-intrusive. However, for the software developer, he can be intrusive and he can do much more interesting things, but we cannot do it at his instead of him. And we are limited because we can measure only from outside and not inside. Another thing, when you do a benchmark, you can do a lot of experiments. The more you do, the more time you spend. And there is a trade-off to find, there is a balance to find between the cost and the degree of confidence between it. And one of the difficulties is that when you do performance benchmark, I would say it is easy because you will just have one or two measures. For dependability, you have several measures and you have to select among them. And so you have to find the most efficient measures according to your application. Not easy. And in this case, I have shown you restart time or response time only. But we have studied also the failure modes of the software. So, just to finish with benchmarking, dependability benchmarks are not mature for the moment. If you look at performance benchmark, they do exist since 30, 40, 50 years from now. They result from cooperative work. They are integrated in the development process, and they are accepted by almost, not all actors. And they are really competitive benchmarks. They push people to do better. If we look at dependability benchmarks, they are still in their infancy. We have some isolated work. Usually, I put a question mark in front of acceptability. Some people accept them, others are still not accepting them. I can say that they are ad hoc benchmarks. Indeed, we are moving from really ad hoc benchmarks to mature benchmark or competition benchmark that can be used by people from industry and by academia. And I have just one or two more slides, and I have been asked to accelerate. Talking about maturity process. Maturity benchmarks are not mature enough, but when we do software collection process, when we do it the first time, based on data collection, data processing, and measurement, we don't have any comparison basis. We don't have any figures. What is interesting is to do it several times and to capitalize the experience, to have some feedback, improve the development process, and so on. And this loop is called software process improvement. So just learn from the past, improve, and do on. And the capability maturity models are based on this. So you observe the software and then you improve. And just here a few examples from published data. I don't know these people. Yes, I know the first one. It was John Musa was involved in this, but not the others. Just from publications for people who used these models. It could be CMMI, but it could be any other. I am not advocating any approaches to improve the dependability of the software. And they all noticed, for instance, the maintenance program has been divided by 10, the system test interval divided by 2, or a new product introduction interval divided by 3. These are examples. All of them agree that they have some benefits. Sometimes they are comparable, sometimes they are not, and you can see that they are not using the same model. This is in-house, quality program 880 in-house model. Concurrent development process from Japan here. Here, Motorola, at the beginning, it was also an internal approach, then they use CMMI, and Return used CMMI. Just to show you that we are not able to improve the software because of some limitation, 10 minus 9, we cannot do it. We can try to improve the development process. So some comment about cost. When we develop a software, a system, being it software or hardware, so we have a basic development cost, You have a cost that will increase if you would like to increase the dependability level, and if you increase the dependability, you will have the rework cost that will drop. All these combined, you can see, after an increase of the cost, total cost, it can be, for high dependability levels, it can be increased highly. If we now take into account and we integrate and we have a maturity process, we can improve the dependability of a software or a system without any cost. This means because I have invested, the investment is at the beginning and at the end, I am improving the quality of my software without any additional cost. This corresponds to the figures I have shown to you. And the ultimate really objective is to have more reliable software, faster and cheaper. And this comes from John Musa also. Okay, thank you. You asked me to finish at 55. It is 55.
Yes, thank you. Punctual. We are right on schedule. So we can take a couple of questions. Please feel free to ask. Sorry, the light. The light, I can't see the floor. Maybe I can ask a quick question. Now, it's really nice to have this dependable, benchmark. In your opinion, is it easy or very difficult to develop a new benchmark for security?
Good question. Easy, no. There is a project currently that is working on developing dependability benchmarks for web-based applications, for intrusion detections on web-based applications. It is not easy at all. They are almost at the end of the project. A benchmark, you have to imagine the kinds of faults or the kinds of vulnerabilities to inject to be able to have representative results. And so the first step is to find representative breaches or representative vulnerability to characterize the attacks. And so for defining a good benchmark, you have to collect data to observe real attacks, then characterize the attacks, group them into classes because you cannot inject a type by attack, and then you have a representative rate or repartition among the attacks. So there is some work that is being done now by several teams in parallel. I cannot say that we have a dependability benchmark for security for the moment, but people are working very hard on this. And there are some publications, for instance, next week, I go to DSN, and in DSN there are some papers related to dependability and security benchmarks. Not easy, really not easy, because you have to do it to convince yourself, to convince the others, and they have to accept it. So, but someone has to start.
Any other question? Here's a question.
You talked about trying to inject faults and then testing the operating systems, and the faults were from the application of the hardware and some sort of thing. What kind of faults are you testing specifically? What kind of faults do you do?
Okay, in the so for the results I have shown, we intercept system calls and we change a system call by another. And indeed, what we have done, you are talking about this. So we intercept system call and we inject, we substitute one system call by another. So we do it intelligently because we can to simulate an application fault. Sometimes the faults were representative. For a good software developer, sometimes they were less representative. But which was interesting is to check how the application, the operating system, the application API would react to this. For this. So the results I have shown are at this level. For hardware, usually, they simulate bit flips. Bit flips, just flip a bit in the memory error or something. But I have not shown this. For devices drivers, it was much more difficult. There is a study, and there is a paper, 2 papers at DSN related to this. So they had to observe the dialogue between the device driver and the operating system, and to select some entries and to change them in an intelligent way to have them representative. It is a long process. It is not easy.
Maybe one last question, because in the next session we'll start right away. So the last question, thank you.
Regarding the software phase, you mentioned that it's about 25% for the malicious aspects and about 75% for the non-malicious aspects. Could you please give us examples for the non-malicious aspects which cause this failure?
When you have a software failure, it is an accidental. So it was not intentional that the software failures. You divide by 5 and it is divided by 5.10 because it's an application. So it was not intentionally malicious. It is not done to hurt someone. But when you attack a web server and when you read the account of someone, or you change the amount, the bank, you visit the banking account and you change the amount and you stole some money, it is intentionally to violate something. So it is really malicious to do some harm or to take some advantage. When it is a hardware failure, nobody takes advantage. Maybe the person who will repair the hardware computer.
One malicious is 7 rate of malicious one. So it's one malicious 75%.
It was for this specific system. This does not mean that this will be the case for all, but for this study that has been performed in France in 2004, it is a paper on this. We are talking about this. In this case, for these institutions, for this case, we have only 24% of faults that have been malicious, intentional. But the others were not malicious. But it could be the reverse also. I think that for web servers, maybe, or using internet, there are a lot of attacks that they may